Good afternoon, everybody. Just to upgrade our activity, I have uploaded on the website all the material consisting of the exercise number 4 materials, a couple of presentations, in particular the presentation on compressible flow I'm talking about today, and I have also included a presentation on the unsteady uncompressible flow. We saw this in detail during in the middle of the course, and you can use the presentation. Unfortunately, this presentation on uncompressible flow is in Italian, but you can easily follow the main content in as they are presented. Excuse me. So I have upgraded these two presentations. You can find this material on the website. And I have also included the last chapter of our note courses on compressible flow. With compressible flow, we have closed the loop of the aeroelastic description for aircraft. And that's all. I hope that this course will be useful for you. I know that the content of this course are not easy in general, but I hope to have reached a right level, intermediate level between physical accuracy and on one side, and the other side, the capability to have practical addressing a recommendation for solving practical problem in elasticity. Okay. So let me. So as I told you yesterday, I would like to have this very last part of the course by using slide, but indeed the content of this part is not so far from the part we considered on uncompressible flow. So I am sure that you have clear most relevant part of this content, but just we have to do some distinction in order to model the compressibility. And so I would like to have with you this last part using the slide. Okay, so let's go and let me share with you my screen. And so this is our compressible flow. Yesterday we concluded our discussion talking about compressibility, and essentially we consider our formulation as formulation in terms of primitive variable, including density, the mass conservation, the Euler equation, so velocity and pressure, entropy, and internal energy as concerning the state space equation for gases, and the included boundary condition. So we included the enthalpy, and the inclusion of the enthalpy is a key point for compressible flow, because the enthalpy plays the role of pressure, indeed. And considering asentropic flow, the enthalpy is very interesting quantity, because we can simplify this part, and therefore we can have that the total differential of the enthalpy is equal to the total differential of the pressure divided by the density, and therefore we can highly simplify essentially the Euler equation. But we have a double simplification. We can express the total derivative of the enthalpy as the total derivative of the pressure, and we have also the capability to express the gradient of the enthalpy as equal to the gradient of the pressure divided by rho. We also introduced the general Lagrange acceleration formula, including this term with the vorticity, and but we had the capability to extend our Kelvin theorem, and therefore using Kelvin theorem, Stokes theorem, and supposing that the vorticity is 0 at initial time, we have the capability also in this case for compressible flow to state that the flow is potential in any time and almost in any point, excluding the wake point, as you know very well. So we have a potential flow in any time, and we can define a velocity potential in this as gradient, such that the gradient of this quantity is equal to the velocity in any point, excluding the wake, discontinuity. And what happens to the Euler equation in this case? The Euler equation, including the meaning of enthalpy, can be rewritten in this term, the Euler equation plus the hypothesis of potential can be rewritten in this form here, and therefore we have the possibility to obtain as first integral of Euler equation the Bernoulli theorem. So at the end we have density conservation, we have the mass conservation, we have the first integral of our Euler equation, which is the Bernoulli theorem equation, and we have a state space equation for the gas, and including that we have a relationship between pressure and density. We have a 1-1 relationship between density or specific volume, which is the same, and the pressure, for example. Okay, so we are ready for obtaining a unique equation in terms of potential. This is the target. We want to obtain a unique equation for potential. So consider the definition of the enthalpy. This is the definition, excuse me, this is the definition of the enthalpy. And we can consider as enthalpy the Bernoulli theorem expression like this in a side and in another side. So here in this equality, we have assumed that the pressure is a function only of the density because of the state space equation. Okay, so we are assuming a special state space equation connecting a scalar quantity like the density and the scalar quantity as the pressure as a unique relationship. So we have this, relationship as given by the role, the chain role, and the density can be, the derivative of the density with respect to the time can be expressed by using the continuity equation. So by using in the same time momentum and mass conservation based on the definition of the enthalpy, we obtain this equation here together. Okay, and here we have velocity potential because we have the velocity, so the velocity is the gradient of velocity potential, and we have this here. We are very, very close to have a final unique equation in the velocity potential, but we have not at the moment all the equation in terms of velocity potential because we have a dp on the rho to be clarified. Now consider, for example, Cartesian coordinate, and here I have developed on the left hand side this operator on the left hand side, and in the right hand side we have the Laplacian operator like here. I am assuming that the sub symbol are partial derivative with respect to zeta, y, x, and time, and so on. Okay, and so it's clear that up to this point, this equation is quite nonlinear equation. Okay, we have to consider a question. The following question: is this equation a wave equation or not? Indeed, this equation is not in the form of a wave equation. Okay, in a wave equation we have typically something like a wave equation. We have a derivative of time, second derivative of time of a quantity like a, and then we have one on the square of speed of propagation of the wave, and a second derivative of time of the same quantity. This is the wave equation. Okay, but we don't have this form at the moment. Excuse me, we have a Laplacian here. I'm sorry, excuse me. Okay, we don't have this form at the moment because we have a complicated operator on the left hand side, and probably in the left hand side we could recognize this as a square of the velocity propagation and this as a Laplacian, but this is not clear at the moment. However, if you see this operator, you can rewrite this operator in this form. The square of the modulus is b dot v, and so this left hand side can be written like the application of a constant velocity dot v. What I mean? I mean the following: if you have to take the square of this quantity and the constant by this, if you take the derivative, if you take the derivative of 1 x squared, you have 2 by x, and you have x as derivative. Okay, and if you take the derivative of a constant of x constant by x, and you take the derivative, you have the same result, you have x. Okay, in other words, if you take a derivative of a square quantity and evaluate its derivative in a point, you have the same result to evaluate the derivative of the reference value by the x, and you will obtain the same result as x0. And for this reason, this can be substituted by this. And if you see this quantity as a constant velocity by the actual velocity, this derivative is now a convective derivative representing the substantial time derivative in a frame of reference which is moving with the constant value of the particle in such a time. What I mean, if you are studying a flow, in general, the velocity particle is a quantity varying in time. And so this, when you take a substantial derivative, like in this form, if you define the substantial derivative as the time derivative plus v dot gradient of this quantity, you are deriving this quantity following the particle with the velocity, the actual velocity of the particle, v. Okay, this is the meaning of the substantial derivative. But if you use another velocity here, and you have this, you are doing the same quantity, but not following the particle, but keeping the value of the particle in the initial time. So you are moving with the frame of reference with a constant velocity, which is the velocity of the particle in such a time. And therefore, substituting this quantity with this quantity, which is the same, you are studying, you have in practice this structure for the velocity potential, and therefore you have a wave equation, but in a frame of reference, which is a moving frame of reference with a constant value of the particle. So you have to define a local frame of reference with the velocity of the particle, and in that frame of reference, your flow in terms of velocity potential is a flow with the same law of a wave propagation. Okay, so in other words, your velocity potential is propagating as a wave with the velocity equal to equal to the square root of dp on the rho, but chi è? Giuliana, scusa, sto facendo lezione, scusami. Ci possiamo sentire? Ok, grazie. Ciao, 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 ciao. So we have a local wave equation, but with the local meaning of this wave propagation, in the sense that you have, first of all, you have a local value of your wave velocity. Excuse me, I have to upgrade my screen. Okay. So we have a nonlinear wave propagation in a double meaning of this nonlinearity. First of all, your local wave is not constant, but this local speed of propagation A is a quantity which is not constant in the mean of propagation, but it is equal to the square root of dp on the r, first of all. Secondly, you are observing this wave propagation in a frame of reference, which is a local frame of reference with the values of the particle in such a point. But you are not following the particle in this frame of reference, but you are moving with a constant translation with a value of your particle as well. Okay, so summarizing, we have a nonlinear equation, and this nonlinear equation is similar but not identical to a wave equation, but is a nonlinear wave equation in the sense that we have not constant velocity of propagation of the wave, and we observe this wave propagation in a frame of reference which is moving not following the particle during the motion. Okay, so boundary condition. For this problem, we have the permeability boundary condition. We have the boundary condition at the infinitive, and as you know, we have to fix our boundary condition on the contact discontinuity, also in the compressible case. And following the same kind of consideration we had for the uncompressible flow, and you did this consideration also in gas dynamics course, we have that first consequence, we don't have jump on discontinuity in terms of vertical component of the velocity. And this is the point. If the flow is isentropic, the jump of the pressure is identical to the jump of the enthalpy. Remember, the relationship between pressure and enthalpy, this here, dH is equal to 1 on rho dP, is applicable also for the jump, and therefore we have that the jump of the pressure divided by 1 on rho is equal to the jump of the enthalpy. And therefore, if you consider the Bernoulli theorem in our compressible form states that actually here, where is it? Okay, the Bernoulli theorem states that if you take this equality in terms of jump, you have that the phi in the point 1 on the tau plus v1 square 2 plus h1 is equal to the same quantity in the part 2, v2 square by 2 equal to a plus h2, and therefore if we have our wake with the discontinuity, and here we have 0.1 and 0.2 up and down, you have that delta H is 0, and therefore you can simplify this quantity, and then you can apply the same kind of consideration on defining the wake velocity as average here between the velocity up and down, and therefore you have the same role as concerning the delta phi discontinuity. Identical for compressible flow. Next, the issue of ideal gases. We have now we have only to solve the point of the wave of the speed, sound speed propagation. We have to express this quantity, the quantity of the A here. We have to express this quantity as a function of phi in order to complete this equation as a unique equation with a unique unknown in terms of velocity potential. We have to express this, and in order to do this, we have to consider our state space state equation for the gases. And remember, we, for a perfect gases, thermically and chemically perfect, we found this two relationship. And so, following the definition of H as equal to E plus P on rho, we can substitute this definition, the definition for E, the definition, and then also P on rho here. And we have this, of course, as function of theta. And again, if you use this again, we have this, and therefore we have this final formula for H. Okay, And now it is necessary to express the local speed of sound as a function, and so we can apply the definition of the enthalpy in terms for isentropic flow. For isentropic flow, we have this, and we can substitute this h by this obtained formula, this formula here, instead of this, and therefore, you know that you obtain this quantity by taking this differentiation. And this implies that you can integrate this is a logarithm integration, and we have that this p tau to the power gamma is constant, and this constant is equal to a, and in this way, noting that a, the constant, okay, is essentially equal to p by rho to the minus gamma, we can to define the a square, the square of the sound velocity, like the derivative of p. So we can take the derivative of p with respect to rho, and we obtain exactly this quantity. So using the previous relationship, we have that this quantity, the square of sound speed, is equal to gamma minus 1h. And so at the end, we can improve our Bernoulli theorem. This is h by this relationship. This is h0. H infinite, sorry, and by this version of this new version of Bernoulli theorem, we have the square of this of the sound propagation velocity, a square, as a function of a sound propagation velocity at infinity plus a perturbation given by the potential. So we have the possibility to express the square of the sound speed as a function of the potential, of the velocity potential. So we have closed our problem, and this is our final equation, where this is a square, and here we have the Laplacian of phi, and here we have the famous time operator that we have interpreted a few minutes ago. Okay, so this is our final equation, also known as full potential equation. As you can see, for the compressible flow, this equation is not linear at all. It's not a simple Laplacian, but we have a Laplacian in the right-hand side here, but we have something else, as you can see. Now, first step, represent this equation in a translating body frame of reference, which is the natural body frame of reference with the aircraft. Okay, so this is our body frame of reference moving with velocity u infinite. This is our computational frame of reference with respect to the air frame of reference. When you take derivative in the air frame of reference, you have this formula, of course, because when you are steady with this frame of reference, you take a time derivative. This time derivative is equal to the time derivative you have when you are an observer here, and plus a convective part, of course, because you are moving with this velocity. So you can transform our original equation. You can consider this left-hand side at this right-hand side of this equation. And so in the left-hand side, this part here can be simplified by introducing this change in the frame of reference and considering that this double time operator, time and time, is equal to this linear part plus higher order term. Of course, when you have this operator with this square, you mean that you have to derive 2 times with respect to the time plus 2u infinite 2 times with respect to time in body frame of reference and space, of course, and you have finally this. However, I know that you are familiar with this notation in your gas dynamic courses, okay? Higher order term. As concerning the right-hand side, you have another kind of linearization. The linear part of this operator is just the multiplication of your speed at infinitive, excuse me, the speed of sound at infinitive multiplied by the Laplacian plus higher order term. And so the first order perturbative solution in the our body frame of reference, and so intending that this time derivative are time derivative in the body frame of reference, is this of this type. Okay, and so we have a linearized wave equation for the velocity potential in the translating body frame of reference. Okay, so we have a linearized form for our differential equation. So we have concluded the first part of velocity potential formulation. Now we have to move for reformulating the problem in integral formulation, because we know the advantage on formulating the problem in integral way, because if the problem is linear, then the integral version of the problem is an integral equation also valid on the boundary and not in the field of the fluid. Okay. Okay. You know this equation. For example, if you consider a steady case, no time derivative, you know that this equation is an equation of this type here. And in the case, of course, of subsonic linearized steady case, subsonic, please linearized. In case of subsonic linearized, we have an equation like this, because you have to cancel this time derivative in the steady case, but you keep this second derivative by u infinite, okay? 2 times, and so you have a Mach number here, and you have the Laplacian here. So the Laplacian contribution plus the Mach number contribution is a unique contribution like this. If you can change suitably your space coordinate, including the famous Planck-Glauert coordinate, and if you use Planck-Glauert coordinate, this equation can be rewritten in Planck-Glauert coordinate in this form here, which is a form of type Laplacian in Planck-Glauert coordinate of phi is equal to 0. So this means that if you have a linearized compressible flow, subsonic in this case, in the supersonic you have a change of sign here in this term. However, if you have a linearized steady compressible flow, this flow is identical to a compressible flow, but you have just to change coordinate. You have transformed your problem by the physical space. The physical space like this. This is the physical space, x and zeta, to the Planck-Glauert space like that, capital X, capital Y. In this new space, you can treat this problem like an uncompressible problem. But is it valid only in the steady case and linearized? Okay. We have excluded, of course, the nonlinear term in our problem. We have cancelled this nonlinear term, but this term may be important, and you know that when this problem, when these terms are important, these terms are important if you want to describe a shock wave discontinuity, for example. And for this reason, sometimes it is possible to consider potential flow, including the shock wave effect, but you are not obliged to include all the nonlinear term. You can also include the first order nonlinear term in order to have a first order description of your shock wave, like, for example, weak shock wave. Okay. So we have a variety of possible model for compressible flow description. The first level of this description is the linearized potential flow. So we can have the transonic small disturbance flows, excuse me for this. And then we have the potential flow. If you include only the linear term, after this description, you can't talk about a potential flow. You have to expand the hypothesis of your flow, and then you are obliged to consider Eulerian flow, Euler equation, or better, Navier-Stokes equation. Okay, so we have different physical model for describing your flow. Okay, so just to recap for linearized differential formulation, we have a unique potential linearized equation, unsteady flow for unsteady flow. We have a boundary condition on the body, the permeability condition. We have boundary condition at infinitive, and we have the boundary condition on the wave. So we are happy because we have very, very similar condition for the compressible flow. The only problem, the novelty is this right-hand side. We have this operator, this time operator in my body frame of reference. Before I have 0 here. Now I don't have 0, I have something different by 0. And I have to organize myself for having, again, an integral formulation. How can we do for obtaining, again, an integral formulation? Again, note that as novelty, we have time variable also present in the equation of motion, not only in the boundary condition. Remember that for uncompressible flow, the only source of unsteadiness was on the boundary condition. The equation, the differential equation to be respected in the field has no time operator, but for compressible flow, we have time operator also in the right-hand side. Okay. And so we have more difficulties in this sense. However, how can transform this differential equation into an integral equation? Okay, this is a very key point in aeroacoustics, for example, and any other field of unsteady aerodynamic. I want to propose you a method for obtaining an integral equation, which is very, very direct, and I don't give you the details of this formulation, but I give you all the indication, and believe me, you easily obtain all the detail developing this by yourself. And I invite I invite all of you to do this for preparing this exam. So the steps are the following. First of all, introduce Pranglauer transformation. So introduce capital X is equal to X divided by L by beta, capital Y as Y by L, zeta by capital zeta is zeta by L. L is a reference length. And beta is this quantity here related to the Mach number. This is for the space, and this is for the time. Introduce our usual undimensional time. This is the classical undimensional time for unsteady flow related to the reduced frequency. We also use a symbol tau instead of capital T. However, this is the undimensional time. Okay, and parallelly, you have undimensional Laplace variable like P, or parallelly, you have the undimensional frequency like kappa. So take the Laplace transform at the zero initial condition of our linearized wave equation. Okay, what we obtain considering this double step in space and time, introducing this and introducing the Laplace transform of such an equation, we obtain this quantity here. We have this operator, and this operator here is the Laplace operator in Pranglauer coordinate of phi tilde. And here you have an expression including P beta, where P is the undimensional Laplace variable that you know very well. Okay, so first step, transform our linear wave equation here in the body frame of reference with these two double step in this form. Okay, as further step, finally, 1, 2, 3, introduce this new quantity phi hat, phi hat. And we introduce this phi hat quantity by the phi tilde, and such that phi tilde is equal to phi hat by, so you have just to substitute this inside here, 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 and here, and here, and so obtaining a new equation in the phi hat. This is the Mach number. This is the X, is the Pranglauer X coordinate, and P bar is this quantity here. So just a change of unknown function. After this transformation, our equation becomes this equation here. It's a very simplified form. This form is a more convenient form. It's simplified. And this is simplified in order to transform the problem in an integral form. In fact, this is our new problem to be solved. It's a strange problem, but this new problem to be solved has an elementary solution to be determined, in the sense that we can find this new G hat green function as a solution of our problem, but not equal to 0, but equal to a delta Dirac. So we have this new problem, and to this new problem we can find the green function for this new problem as a function able to solve this as equal to delta Dirac in x star with no, remember, no boundary condition as typical for the green function solution. And do you remember in the uncompressible case we have this equal to this physical x minus physical x star, and we have as a solution a g, the standard solution that you know, which is -1 by 4 pi amplitude x minus x star. And this is an analytical solution of this problem with no boundary condition. Here we have the same, and this new problem, generalized new problem, has an analytic solution. If you are interested on this, you can find a demonstration of your note that this is the analytic solution of our green problem. The g hat is such that it is equal to g0, and this is g0 in Planck-Glauer coordinate, by e to the power minus pi bar r. The demonstration is done just taking this quantity, put inside here, and check that this identity is verified. Okay, so we have a green solution for the associated dual problem. The dual problem satisfies not the original problem, but the original problem is equal to a Dirac forcing term, but with no boundary condition. Okay. Okay. At this point, we have this equation. My original equation transformed, and we have the elementary equation with G, and we can combine these two relationships in the usual way. How? We can multiply, we can multiply this quantity, all this equation by G, all this equation by phi, the famous cross product. Then we take the difference and then integrate, and this is the result. The only difference with respect before is that now we are playing with very strange variables which are not physical, but we have time to go back to the physical and the original quantity because we know the transformation. This is the transformation. This is the magic transformation that we allow to me to go back to the original quantity here. Once I have determined this. Okay, so don't worry. So we have now to solve this problem, and we can apply here the Gauss theorem, just rewriting this quantity in a divergence form. In fact, we can consider the second green identity as usual. I want to skip this part because you know very well the green identity. This is the green identity which allow to express this in a divergence form. And therefore, our original problem is written here. The original problem, which is this here, is rewritten in the boundary. as an integral, not in the volume of the fluid, but in the boundary, in this way. This is the boundary, and the boundary is composed by the surface in Planck-Glauer space, please, surface. So this zero means are reminding that we are working with the Planck-Glauer quantity. So we have S0 on the body plus S0 at infinitive plus S0 on the wake. And we have this famous quantity, but for the hot quantity only. The standard domain function that you know very well, and so on. And at the end, we have this. The domain function in the Planck-Glauer space applied to my strange variable, phi hat, is equal to an integral on the boundary of the body at infinitive and on the wake of such a quantity here. My final maneuver is to go back to the original coordinate. And for go back to the original coordinate, I have simply to remind this formula, mpx, and so we have just to remind this. As we have that phi tilde is equal to phi hat to m e to the power mach px. Okay, and if you do this by this, we have the following. I want to stop here for a second because I want to comment this final formula that we have obtained. So let me do this break for everybody. A few minutes. Thank you. Chiedo scusa se sono andato troppo veloce. Se vi ricordo anche però che voi avete tutto, avete la registrazione, avete queste view graph scritte, insomma avete un po' tutto quanto. Qua c'è Paloni che ha detto che non è riuscito a scrivere. Se mi dice che cosa non è riuscito a scrivere possiamo tornare indietro senza problemi. Comunque i passi che abbiamo fatto sono gli identici passi che abbiamo fatto per i flussi incomprimibili. Io volutamente li ripercorro e vado un po' veloce anche perché molte cose sono simili, a parte ovviamente alcuni dettagli importanti che sono quelli prevalentemente dovuti al fatto che adesso c'è l'entalpia che sostituisce la pressione nel teorema di Bernoulli. Abbiamo visto come questa entalpia così definita consente la definizione dei flussi potenziali non stazionari comprimibili, consente sempre la definizione dell'entalpia, la ridefinizione della scia e delle condizioni al contorno sulla scia che sono identiche, linearizzazione, scrittura dell'equazione del potenziale come equazione delle onde nel sistema di riferimento corpo. Però ovviamente tutto questo avviene perché è possibile una linearizzazione del problema, che abbiamo fatto, perché le equazioni in termini di potenziale di per sé sono non lineari. Stavolta ok, ci siamo raccontati questa cosa, quindi siamo arrivati ad una forma dell'equazione delle onde. Adesso stiamo applicando sull'equazione delle onde una metodologia che ci consente di trasformarla in un'equazione integrale. Non è nella forma Lagrangiano di φ uguale a 0, ovviamente, ma è nella forma Lagrangiano di φ meno 1 su c quadro, cioè la velocità di propagazione a infinito, uguale all'operatore di derivata convettiva o infinito 2 volte. Come facciamo? non sappiamo applicare il metodo integrale così, non è così semplice. Allora abbiamo fatto una trasformazione di quell'equazione in modo tale da renderla trattabile dal punto di vista del metodo della funzione di Green. Cioè abbiamo fatto in modo tale di riscrivere in questo modo la nostra equazione. In questo modo qua l'equazione può essere trattata come se fosse la Laplaciano di φ uguale a 0. Infatti il metodo della funzione di Green, che pure si può trovare in questo caso, è tale da semplificare questo termine, non lo cancella, perché se voi fate questo per questo meno questo per questo, ovviamente il termine φ cappello, P segnato quadro, G cappello si cancella. E vi trovate solamente questo termine qua. Va bene? E quindi abbiamo le porte aperte per poter scrivere anche qui un'equazione integrale. Un'equazione integrale di contorno. Silenzio assoluto. Il baratro.
Professore?
Sì.
Invece la trasformazione di coordinate che abbiamo fatto per sì,
no.
questa φ in, φ in funzione di φ cappello
Sì.
ha cioè nel senso è un artificio solamente matematico.
È un artificio fino a un certo punto però, ma è, riprendo un attimo, è quella cosa che ci consente, ecco, è quella cosa che consente, un momento, ecco qua. Allora, se io, ci sono tre fasi, vede, 1, 2, 3, se facessi solamente le seconde due fasi, cioè passassi dal tempo fisico, la frequenza o variabile Laplace fisica a quella dimensionale e prendessi i coordinati di Prang-Laubert, mi ritroverei, e facessi poi la trasformata di Laplace, mi troverei un'equazione, che la mia equazione originaria, nella trasformata di Laplace della variabile originaria sarebbe di questo tipo. Vedi, ci sarebbe un 2p, ci sarebbe un p quadro, non ci sarebbe un termine unico. Allora, per semplificare questo termine, fare in modo che questo termine sia zero, quella trasformazione di coordinate che viene introdotta è tale che, se fatta, consente di passare da questa equazione, aspetti, poi la cancello, consente di passare da questa equazione, no, che miseria, qua,
Sì.
a questa equazione qua, ok? Che è molto più, ha una forma laplaciano meno costante per laplaciano della funzione meno costante al quadrato per la funzione, che è una cosa equivalente ad avere un laplaciano uguale a 0, perché poi la costante, la parte diciamo costante rispetto alla differenziazione spaziale, le si cancella quando fa il prodotto incrociato. Quindi è un cambio di incognita dalla φ tilde, che è quella, la trasformata di Laplace della variabile originaria, alla φ cappello, che è un artificio matematico per semplificare l'equazione. Diciamo che il matematico avrà detto: come devo fare per fare in modo che da questa equazione qui ottenga questa qui? Ok?
Ok.
Va bene? E ha
Ok.
trovato questo artificio.
Cioè il fisico invece avrebbe qualcosa da dire
Il
a
fisico
riguardo?
glielo dico io come avrebbe fatto, no? Glielo dico bene. Lei per caso farà l'esame di aeroacustica?
Non l'ho messo
No.
nel piano di studi,
Vabbè.
però
Allora, il fisico avrebbe fatto questo. Che cosa c'ho? Un'equazione delle onde, che è spazio-temporale. Cerchiamo la funzione di Green, avrebbe detto direttamente, cerchiamo la funzione di Green tale che il laplaciano di G meno 1 su a infinito, derivata rispetto al tempo, più u infinito, derivata rispetto allo spazio, al quadrato di G, sia uguale, attenzione, a un delta di t per un delta di x, doppio delta perché questo è spazio temporale, c'è anche il tempo adesso. E cioè, che cavolo è questa soluzione? È la sorgente acustica che si muove con velocità infinito e che fa, è la schicchera che si muove, perché la schicchera perché lei dà nel tempo un disturbo di sorgente di massa e poi lo dà nel punto x star mentre questo punto si muove. Quindi è la sorgente acustica. Doveva trovare onestamente, come funzione di Green duale al suo problema, la soluzione della sorgente acustica. Sto nell'intervallo delle lezioni, dimmi, veloce Sara. Ok? Perfetto, ok? Ciao, 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 ciao. Oh, aspetta, dove? Quanti in una pagina? Ah. Ha capito? Cioè avrei dovuto trovare la soluzione di Green corrispondente a questo problema, che è un problema di propagazione ondosa, e quindi la soluzione della sorgente acustica che emette nel punto X star che si muove con velocità infinito. Che è esattamente quello che fate in gas dinamica nelle prime lezioni, no? O no? O mi sbaglio?
Sì, 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 quando fa pure il discorso del
Certo.
cono di Mach, sì,
Quindi
sì.
bisognerebbe fare un problema del metodo diciamo, di contorno come integrale. Mannaggia, scusi. Sì, dimmi. Pronto? E niente, ti stavo dicendo che quanti in una pagina? Più di una pagina? Quelle, due? Ok, va bene, va bene, va bene, ciao, 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 ciao. Chiedo scusa. Quindi sarebbe stato un problema di soluzioni di Green non solamente come integrale spaziale, ma anche temporale.
Ok.
Ok? Perché? Perché adesso abbiamo una equazione di Laplace che non è più un'equazione di Laplace, è un'equazione di Helmholtz, diciamo. È un'equazione delle onde nel tempo, un'equazione di Helmholtz in Laplace. Quindi con Laplace eliminiamo il tempo. E
Ok.
poi ulteriormente questa trasformazione di coordinate mi rende l'equazione Laplace trasformata, me la rende nella forma equazione di Helmholtz, cioè operatore laplaciano sulla funzione meno costante per operatore laplaciano uguale a 0. Con
Ok.
questo artificio matematico si ottiene la stessa cosa che si fa in acustica, cercare la soluzione elementare dell'acustica, che è una sorgente di disturbo che si muove. Una sirena di una tombulanza che si muove in un punto.
Sì, sì, sì.
È chiaro?
Sì, credo di aver afferrato più o meno il concetto.
Dopodiché però i casini lì ci stanno nella parte temporale, perché lei deve fare anche l'integrale nel tempo. E l'integrale nel tempo, facendolo duale, è un po' complicato perché così come c'ha un x e un x star, c'avrà anche un tempo t e un
Io
tempo
ci
t
sta.
star. Ha capito? Cosa
Sì,
che mi
sì.
piacerebbe tanto fargli vedere, però non ho il tempo fisico. Questo artificio matematico, seguendo una procedura puramente matematica, fa le stesse cose, non ve le fa vedere, però ottiene lo stesso risultato. Ok?
Ok, sì, più o meno credo di esserci.
Ecco.
Grazie mille.
È un po' un escamotage, capito? Per poter ottenere lo stesso risultato con breve tempo, con minor tempo, diciamo.
Sì,
Va bene?
sì, sì. Grazie.
Prego. Volevo farvi, se per caso fossimo tutti quanti parlanti in lingua italiana, volevo l'ultima lezione dar farvela in italiano, ma insomma mi sa che non è possibile. Abbiamo un ospite anche straniero con noi, non ho verificato, penso di sì. Sì, sì, ok, va bene.
Professore, invece nel flusso transonico alle piccole perturbazioni poi lo risolviamo in maniera iterativa.
Domanda interessante. Il flusso transonico alle piccole perturbazioni è un termine noto a destra, cioè se lei va a vedere, questa,
Sì, che è fix.
allora se ci avesse un termine di questo genere, ok, lei ci avrebbe un termine qui, no?
Sì.
Che esiste, che c'è. Quindi avrebbe Laplaciano meno questo. L'equazione delle onde si chiama, tutto l'operatore delle onde si chiama D'Alambertiano. D'Alambertiano di φ, invece di essere uguale a 0, D'Alambertiano di φ uguale a questo termine. Allora lei, quel termine lì, che è un termine, come si dice, risorgente, lo può pensare presente a destra, invece di 0, no? Quando farà tutte le sue trasformazioni, ci avrà qualche cosa qua invece di avere 0, va bene? E allora, quando fa la differenza e fa l'integrale, qui invece di avere solamente questo pezzo qua, ci avrà pure un pezzo con integrale. Questo pezzo qua le dà il valore della funzione. Allora, il pezzo a sinistra le dà il termine al contorno, il pezzo a destra le dà il valore di φ in x star con la funzione di dominio, giusto?
Sì.
Più un altro pezzo e le rimane l'integrale di volume. L'integrale di volume dove? Fatto dove? Beh, fatto tutto il volume. Però chi ci sta lì? Ci stanno i termini non lineari. La domanda è: dove sono importanti i termini non lineari in un flusso compressibile? Sono importanti dove ci sta l'urto, o no?
Sì.
Quindi, in realtà, quello che succede è che lei ci avrà questa cosa qui, ok, più un integrale di volume, chiamiamo sigma i termini non lineari, sigma g in dx, ma questo qua sarà importante non su tutto quanto il flusso, ma per esempio qui intorno.
Ok.
E qui ci stanno i termini non lineari. Quindi questo integrale di volume, che dovrebbe essere su tutto il flusso e che non vi farebbe affatto risparmiare, diciamo non vi farebbe godere del vantaggio di avere un'equazione integrale di contorno, perché vi obbligherebbe a integrare tutto quanto il volume, giusto? Di fatto però lei lo fa e lo estende solamente dove i termini non lineari, sigma, che ho chiamato sigma, sono importanti. In un flusso transonico, le piccole perturbazioni sono importanti intorno all'onda d'urto.
Ok, Però poi qua interviene pure, diciamo,
Sì,
una...
perché il problema quando sta l'onda d'urto è
esatto.
l'onda d'urto il problema è al solito, quindi shock capturing, tocca sapere dove sta, eccetera, eccetera.
Ok. Sì, sì, ho
Ok?
capito. Sì, grazie ancora.
Niente. So, ok. Ok. So, after this position, we have the capability to consider this final integral equation here. This final integral equation here. And next, we have to go back to the original unknown. Andrea, scusa, sto facendo lezione, ti posso chiamare? Ma figurati. Ciao, ciao, ciao. So this, I can go to the original unknown. Phi hat, excuse me, this original unknown. As phi, just going back, inverting this easy relationship, like e to the minus mach p bar x by phi hat, phi tilde, and then we can put this here and here and here. Okay. So here we have the original coordinate tilde, 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 okay, and but we have also other quantity, other quantity related to this exponential, of course. And next we have to develop our p bar. This p bar, remember, is related, is a definition here for p bar, and it was equal to mach p by beta. And then my integral equation after this substitution for p bar, we have this final equation with, we have G0, remember, is -1, is very similar to G, but in Prandtl-Glauer coordinate, 4 pi capital X minus capital X star, vector. And R is the distance between, R is this exactly. P bar is P bar, and so this is our final relationship. And look the structure of this relationship. This part here is identical to the uncompressible flow. We have the Laplace transform of phi, we have G0, and this capital N is the normal, but in the Prandtl-Glauer space. Okay, so this is normal in Prandtl-Glauer space. And this is it, the novelty the novelty of this formula is in this part here and in this part here, an exponential, multiplying all the quantity inside the integral. Okay, now as concerning this part here, you know that you have p by phi tilde, and so in time domain you probably have a time derivative of the potential. Okay, as concerning this exponential part here, in Laplace domain, the multiplication of a function depending on Laplace variable, a multiplication to e to the power minus p Laplace variable theta is in time domain a quantity delayed of the quantity theta. So this capital theta is representing a time delay, again a time delay. I am not talking about the wake. I am not yet introduced the wave mechanism. I am integrating on the body in Planck-Lauert, on the infinite in Planck-Lauert, on the wake surface in Planck-Lauert, and I have yet a term with an exponential. This theta is a quantity which has this kind of structure here. And if you go back to the time domain, you realize that this quantity is a compressibility time delay. So it's a delay due to the time necessary for a disturbance by a source to reach the receiving point. Okay, so you have a delay related to the compressibility, and this is the novelty. You know probably this draw. This draw is a draw you used in gas dynamics, and if you have a source of disturbance moving from here to here with the velocity, and if you give your disturbance in this time during the disturbance propagating here, you are moving here, and when the disturbance is reached this point, you are here. Okay, you know this. And after a very elementary Pythagorean consideration on this, you can easily demonstrate that the time theta necessary to the disturbance emitted here to reach this point x star is a solution of a second order algebraic equation, and the final result is that this delay theta, note that I have not a capital theta here, I have a theta, is given by this algebraic quantity. If you undimensionalize this theta in a capital theta by this kind of dimensionalizing quantity like U infinite and L, you will exactly obtain this expression here. So demonstrating that this capital theta in an undimensional form is representing exactly the time necessary by a disturbance of the velocity potential to reach a receiving point after emitted by a source point. Okay. And so this is our final equation after introducing the wake. And so I have splitted from here this tribal contribution, this, and this. This is 0 to infinity again. So you have to distinguish the integral on the body on the wake. On the wake, you have the same kind of consideration we had for a compressible flow, and therefore we have a body integral and a wake integral. And this part in the wake is skipped because in the wake, delta, the derivative of delta phi on the end is 0. And so you have the delta quantity on the wake only in this form. The novelty is this term here. The novelty is this term here, and the novelty is the delayed here. All these quantities are delayed, and therefore when you represent this integral in time domain, you have that the potential in the Frank-Glauer point x star in a time t, present time, is equal to the integral of such a quantity, but in the previous time t minus theta, previous time. So the solution that time depends on what happened in previous time, and this is the effect of compressibility. Okay, in the body frame of reference, of course. So we have an integral representation of the solution if x star is in the fluid domain, and if the solution on body and wake boundary is known. So this equation is a representation of the solution in a time, in a point of the fluid. If you know the solution, as usual, if you know the solution on the body and on the wake. In this case, we have that domain function E is equal to 1, okay? But the same equation is a compatibility condition for the solution if x star is on the body surface, and therefore the velocity potential solution is unknown in the point x star and on the body surface. The function g0, the g0 on the end, theta and theta are all known functions. Note that the delay, the time delay theta is a quantity depending on the geometry, of course. And so the solution depends only by the input in terms of boundary conditions. So we have this boundary condition, input, and by the knowledge of this input boundary condition, we have the output phi. How? Just to discretize our problem with a panel method. And so we have the following. We have that the solution in a time t, capital T, in a point k depend on the solution in the previous time t minus a delay, and such a delay, look, the delay depends on what? The delay depends on the x star receiving point and x emitting point, both. So in the discretized vision, this delay depends on a double index. Yes, kh. K is the index of the receiving point star, and h is the generic point of the current panel. Okay. So we have an amount of compressibility delay to be evaluated, but are all known on the basis of geometry of the solution. Okay. And again, we have just to define this coefficient B, like C, like D. D is the novelty. D and G are the new coefficient involving this term with the time derivative. This is the novelty. The other term B, C, and F are identical as before, but in Frank-Glauer coordinate. And we have source term, doublet term, like before, doublet term on the wake, and we have new term like this and this as d and g term associated to the time derivative. Okay. All these coefficients are generally not depending on time, but are generally time depending if the body is moving with small oscillation. So are not depending on time is the body is moving with small oscillation around the reference configuration. Wake. The wake discussion is actually the same, but for the wake, we have just to add a delay contribution. So the delay mechanism of the wake is a further mechanism with respect to compressibility delay. So we have another further delay mechanism associated with the wake, just to be added to. In fact, for the wake, I remind to you that we have the delta phi in the wake here, in this point, is equal to the delta phi at the trailing edge in the previous time, capital pi, with capital pi is equal to the time necessary for the point to move from here to here by u infinity divided by L, okay? And therefore we have this kind of undimensional quantity, okay? So just the same, and therefore we are able to modify improve our discretization, space discretization mechanism, including the wake mechanism delay. So this capital pi is a further delay with respect to the compressibility delay. So we have the compressibility delay, but on the wake we have to sum also the delay associated to the mechanism of the wake. Okay. Stupid operator S, as you know, in order to express the jump of the delta phi at the trailing edge as generic depending on the potential on the body surface. And so at the end, we have a final time domain relationship between the velocity potential, including all this delay mechanism. And this is the input, the non-input, and these are the output in the point and the derivative of the output in the point. Okay. In Laplace domain, we can obtain by this time description a Laplace domain description, take the Laplace transform of this expression, and so we have an exponential mechanism of delay, and here on the wake we have a double mechanism of delay for compressibility and for the wake delay mechanism. As final formula, we have our E2 operator right here. That's all. We have a Y matrix here depending on P, Laplace variable, and we have a known matrix again depending on P. In this case, note that also zeta is depending on P for compressibility. And our final E2 matrix is the matrix transforming the normal wash vector in the potential vector E2. Okay. Note that this matrix depend on P, but depend also on the Mach number. How this depend on Mach number? Can you see the dependency on Mach number here? How this quantity Y, zeta are depending on Mach number? We are in Brand-Glauer space. and theta depend on Mach 2. Okay, so all this quantity depend on Mach number, and all the coefficient dependent on Mach number because they are obtained in the Planck-Lauer space, transformation space. Okay, and so this is the E2 matrix depending on P and Mach number, or in MC Nastran code depending on reduced frequency and Mach number. C MK aero card Mach and reduced frequency. Okay. And what about the other matrix? What about the other matrix? We have E2, but we have also E1, E3, and E4. Huh? Are all these depending on Mach number? Not yet. E1 depend on boundary condition, and the boundary condition transforming the modal coordinate in normal wash don't depend on Mach number at all. Again, the E4 operator transforming the CP in generalized coordinate by just projecting the pressure field onto the mold shape does not depend on Mach number at all. So the only matrix component depending on Mach number are E2, and we have demonstrated this, but probably also the Bernoulli theorem or something transforming the velocity potential in coefficient, in pressure coefficient. So we have to analyze this last point together. Okay, let's go. Let's go. E1, I skip E1 because E1 is standard. It's not depending on Mach number. I'm skipping, okay? Blah, 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 blah. Speed, standard. Does not depend on Mach number. Okay. And E3. Okay, E3. From the velocity potential to the pressure coefficient. Bernoulli theorem. We have a problem, Houston. In the body frame of reference, this is our Bernoulli theorem, including the local value of the speed of sound. And so we don't have the pressure. In the airframe of reference, we have this, okay? Now, first, we can obtain the ratio from, we can obtain this, modifying this formula, so we can obtain this ratio by Bernoulli theorem and express this here. Okay, okay, but this is not the pressure. Okay, the pressure coefficient is defined as this. As you did in gas dynamics, it's better to represent this in terms of this ratio, and so in terms of Mach number and the ratio between the pressure in a point and the pressure at infinity. Okay. Now we have to relate. Now this value with this ratio. This is the connection. This connection is very, very familiar for you if you consider isentropic transformation. We did this for a square and for a infinite. Take the ratio between this and this, and you have this relationship. So this is the relationship, which is the connection between this and this. Okay. Okay. So I am expecting that this is not linear. In fact, it is non-linear. So look to the relationship giving the pressure coefficient as a function of velocity potential. We have a non-linear relationship. Okay, unlucky day. But we need to have a linearized form because we want a matrix E3 transforming the velocity potential into the CP as steady quantity, but in a linear way, not in a non-linear way. So please try to linearize and see this relationship like a relationship like this, like 1 minus beta to the power gamma divided gamma minus 1 as a power. So this is beta. This is beta. Assume this is not the previous beta, this is another beta, just to, if you expand this function as a function of beta and you consider beta as a small perturbation of your problem, small, so you have that this is almost equal to for beta equal to 0 you have 1, and then take the derivative and you have plus minus gamma on gamma minus 1 by beta plus higher order term. If you expand this in this way and put inside here, you have, oops, you have this. And what is this? This is the Bernoulli theorem for uncompressible flow. So we have demonstrated that the linearized form of Bernoulli theorem for compressible flow is the uncompressible form of Bernoulli theorem. Huh? I repeat. The linearized form of Bernoulli theorem in compressible flow is the form of Bernoulli theorem for uncompressible flow. Okay? And so we have this. The same form as incompressible flow. Okay, like this, you know very well. So E4 does not care about compressibility, just identical operator. And so we have finished. Comment. The aerodynamic operator for a linearized compressible flow around a translating body has a dependency on Laplace variable S of second order maximum polynomial type, in the sense that the aerodynamic has a behavior that is equivalent to mass, damping, or stiffness terms, but it also has a transcendental type dependency, and this is physically due to the delay mechanism due to the wake and compressibility effect, the novelty. Transcendental type. Okay. The aerodynamic operator for a linearized compressible flow around a translating body parametrically depends on the flight Mach number through the aerodynamic coefficient as a source, doublet, delays, and Pranglauer transformations. Okay, so we have the following. We have here our E matrix as a function of P and Mach number in Laplace domain, or as Nastran says, E as a function of reduced frequency and Mach number in Fourier domain, if you use PK method for stability or something like that. Okay. This is the very last, very last item for these courses. Lifting surface. Question: is it possible to simplify our formulation in the case we have a very thin wing? Yes, it is possible. So we have an equivalent lifting surface for compressible flow. We have just to write our formulation for very thin body. this body is a thin wing plus a wake, reduce it to a surface like this, but incompressible flow. And we have just to consider that at the moment we have new term in the formulation, which are this term here and this term here. Okay. And look, we have included the wake and the wing in a unique domain, like this, unique domain for body and wake. And consider the derivative of this product. We have two terms in this, and so we can compact this in a unique term, also considering that on the wake we don't have this term here. Okay, and so we have only these two contributions, this and this, because this contribution here is 0 for body and wake. No permeability in the body and in the wake. So we have only these two terms, and these two terms are compacted in a unique term like this. Okay? Okay. Oops, we don't have any boundary condition. So we are obliged to take the derivative with respect to zeta. And so we move from this potential formulation to this velocity potential normal wash term here. So we take this derivative with respect to zeta star. So we have a second order derivative with respect to zeta star inside the integral. And here we have from the potential to key. Again, we want to see a delta pressure inside. And so we have a complicated integration by part, but not so complicated. We have to integrate by part this term. And after integrating by part this term, we can recognize a pressure, a delta pressure inside this expression. And the final integral equation is an integral equation connecting the delta Cp within a normal wash by using a kernel function. And since the delta Cp is 0 on the wake, we have only an integral on the wing. And that's the motivation in Nastra for compressible and uncompressible flow. We have just to decide the panel discretization on the wing only, not on the wake, because in Nastra, a lifting surface method is used for unsteady aerodynamic. This lifting surface method is also known as DLM, doublet lattice method. Why doublet? Because we have only doublet term, only G and not yet G, excuse me, only the G on the zeta, so only doublet elementary solution and not source solution. Okay, and this is used for this kind of operator, and for with this formulation we have a direct connection between delta Cp and normal wash. At the end, we have a unique matrix including the E3 contribution and E2 contribution, just transforming the normal wash into the delta Cp, directly skipping the intermediate step of the velocity potential here. Finished. Okay, so I have concluded this course on aeroelasticity, and as you see, this course is theoretical and practical in the meantime, because this allows you to critically do stability analysis of aircraft wing configuration, and you realize this by your last exercise number 4. But we traveled starting from the panel flutter model, the section model, the wing model, and so we considered all the background from the structural dynamics, and we built all the background for the unsteady, uncompressible, and also compressible linearized potential aerodynamic. Putting together these two models, we studied together the possibility of study the stability problem and the response problem for an aircraft. Of course, this course was focused on aircraft. So we focused on external flow occurring to translating aircraft. And we studied both steady solution and unsteady solution. But we study linear problem, and therefore the unsteady solution around any kind of steady solution is the same for the system. And therefore it's not essential to consider a deformed steady configuration for studying the stability. We study the stability at 0 angle of attack with no problem. I am repeating a lot of concepts for you. Important concept. Okay, so now I would like to have by you some comment about this course. Probably is not this course. We will have call for exam on January the 8th, and the practical organization for the exam is the following. On January the 8th, we have a very fast of about 1 hour, 1 hour and a half test, written test. I will communicate to you if this test is on the morning or in the afternoon. In the same date, I have another exam, so I have to split the exam on aeronautical structure with the sum of the elasticity. However, for the elasticity, on January the 8th, we have a written test, and I will communicate you the time for this test. This test is a theoretical part of the course, and then you have an oral part, and the oral part is composed by other question on theoretical issues of the course, and finally a question about the project you have developing the exercise I assigned to you. I finished. I would like to have by you some feedback. This feedback could be bye-bye or comment, I don't know. Thank you.
Beh, è stato molto istruttivo, professore.
Distruttivo?
No, istruttivo.
Ah, ok.
Distruttivo a volte, però vabbè.
Come si può migliorare?
E allora, forse un po' la prima parte, quella di dinamica strutturale, diciamo, capisco che non tutti hanno lo stesso background, però diciamo che rispetto al corso di strutture non aggiunge tanto rispetto a quanto già fatto.
E se non l'avessi fatta, per chi fa l'esame senza aver fatto quella roba, come faccio?
Sì, 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 ma ho premesso, infatti, capisco che il background non è lo stesso, perlomeno
E poi di quante ore stiamo parlando? Cioè,
beh, è
stiamo parlando di
stato,
4 ore, no? Di 2 lezioni, 2 o 3
oddio,
lezioni.
beh, è stato, adesso non ricordo benissimo, però una settimana e mezza più o meno di lezione, poi non mi ricordo precisamente. Però ecco, per il resto molte cose interessanti. Poi certamente l'argomento è vasto, ci stanno tanti fenomeni, noi comunque ci siamo limitati alla fissa, ad esempio, però immagino che comunque bisogna prima
Però
imparare a
avete
camminare.
capito, cioè la fissa l'abbiamo fatta, credo approfonditamente, credetemi, è un corso mediamente rispetto a quello che si becca, si trova nel mondo, è un corso abbastanza approfondito quello che facciamo noi dal punto di vista teorico. Però doveste trovarvi di fronte ad altri problemi, cioè per esempio ad una rotante, avete capito che quali sono questi problemi, cioè la rotante avete una scia che non è fissa, che ha una geometria completamente diversa e quindi nel momento in cui vi influenza il problema a monte lo fa. Diciamo, avete capito che ci sono delle cose standard da fare? Ci sono, uno, da tradurre le condizioni al contorno del solido che si muove in condizioni, diciamo, l'output della struttura deve diventare l'input dell'aerodinamica, quindi
Ok.
devono diventare condizioni al contorno dell'aerodinamica. L'aerodinamica produce un campo di pressione intorno al corpo che entrano, cioè il meccanismo spero
Sì, sì.
generale sia chiaro e quindi questo vi consentirà in futuro di affrontare, credo, un qualsiasi problema di interazione fluido-struttura che troverete anche se vi troverete a trattare delle pale di turbine.
Sì, sì, sì,
I metodi
ma
sono quelli. I
sì, sì,
metodi
ma poi ovviamente, cioè, ripeto, comunque bisogna prima imparare a camminare, poi a correre, quindi
certo, no, ma
è giusto.
vorrei sentire anche qualcun altro, molto sinceramente e semplicemente se avete qualche idea e poi insomma vi lascio. C'è qualche altro commento?
Professore, per me è stato veramente un corso completo, dico sia dal punto di vista teorico, cioè veramente abbiamo fatto tutti i passi uno ad uno, e poi anche dal punto di vista applicativo, cioè poter applicare passo passo la teoria è stato, a mio parere, eccitante, devo dire la verità.
Addirittura. Ah, vabbè. Ma mi fa piacere che abbiate trovato anche una passione nel fare le cose, perché la passione poi principale sta nello scoprire che tutto il percorso teorico che avete fatto fino adesso, insomma, vi serve a qualcosa per capire, insomma, un po' meglio certe cose, no? Quindi quella è la soddisfazione più grande, credo, che ognuno di voi
Sì,
può.
decisamente, decisamente. Volevo dire una cosa del genere. Infatti la ringrazio tanto, professore.
Va bene, ma dovete ringraziare voi stessi più che altro, perché poi alla fine vi trovate a fare queste cose, insomma, ed è una soddisfazione nel vostro percorso formativo.
Sì,
Va
certo,
bene,
certo, professore, e noi dobbiamo lavorare, però un buon professore fa la differenza, insomma, è un'altra cosa.
va bene, grazie. E niente ragazzi, buon lavoro e tanti auguri di buone feste natalizie a tutti, buon Natale e buon anno a tutti quanti e ci vediamo insomma con calma alla prova quando vorrete organizzarvi. Gli esami sono stati già tutti quanti fissati. Se avete qualsiasi dubbio, allora se volete che fissi delle date per le spiegazioni lo posso fare da qui nel corso, cioè io pensavo di fissare alcune date, metterò magari un avviso oppure possiamo già fissarlo adesso, non so, possiamo fare il 28, 26 o il 27 o il 28, fisso un giorno per domande, per dubbi se ne avete.
Io, professore, una domanda ce l'avrò sicuramente, quindi per me andrebbe benissimo.
Va bene, allora cerchiamo di fissare una data, che potrebbe essere una data tra Natale e Capodanno, insomma, una cosa del genere. Va bene?
Professore, scusi.
Sì.
Senta, ha novità su quel problema della sovrapposizione delle date con l'esame del professor Coppotelli? Che le avevo detto qualche giorno fa.
L'esame del professor Coppotelli
Che avevo detto che avevo visto che diciamo, tutte le date dell'appello di aeroelasticità coincidevano con quelle di experimental testing for aerospace tractors. Quindi lei mi aveva detto che doveva vedere un attimo.
Devo sentire Culla che ancora non riesco a sentire, sì,
Ah.
adesso lo devo chiamare. Aspetti un attimo che... Ancora non sono riuscito a parlarci con il professor Culla, va
Ok.
bene.
Va bene.
Grazie.
Grazie, arrivederci, auguri.
Arrivederci, auguri a tutti ragazzi.